Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you've ever pictured what a truly sustainable energy future might look like, chances are space-based solar power, or SBSP, was part of that picture.
Oh, absolutely. It's this ultimate high-tech vision, isn't it? These gigantic solar arrays up in orbit way above the clouds, soaking up sunshine 24/7.
Constant unlimited sunshine. No night, no clouds, just pure energy beamed back down to Earth.
It really is seen as a kind of holy grail for clean energy. I mean, think about it. Solar power down here on the ground is always dealing with nighttime, bad weather, the atmosphere scattering light. It all cuts down efficiency.
Right.
But a satellite parked in geostationary orbit, GEO, that's bathed in intense sunlight constantly, it could provide reliable baseload power day in, day out.
And, this isn't just science fiction anymore. It's moving towards reality pretty fast. We've seen some big steps lately.
Definitely.
Like the Caltech Space Solar Power Project, the SSPP demo. That really showed it's possible, fundamentally, to send usable power wirelessly from orbit down to a receiver on the ground.
That was a huge proof of concept. And it's not just Caltech. There are pilot projects bubbling up elsewhere, too. China, the UK, Japan. They're all looking seriously at this.
So the whole conversation has shifted, hasn't it?
Exactly. The basic physics, they work. The question isn't really if we can do it anymore. It's more like, okay, how much power can we actually realistically deliver? Considering the costs, the logistics.
Which brings us perfectly to the analysis we're looking at today. We're diving into this really interesting new paper. It's in Acta Astronautica by some Italian and German researchers.
Right. And they set out to do something specific. Calculate the absolute maximum potential power you could get from a whole constellation of these SBSP satellites up in GEO, designed purely for energy.
And what's fascinating, what really caught my eye, is how their findings kind of flipped the script on what we thought the main problems would be.
Yeah, that's the core of it. For decades, I think most people, even engineers, assumed the big hurdles would be, up there, technical stuff.
Like dodging space junk, or just the challenge of building these enormous structures in zero-G.
Or the efficiency of the power beaming itself, getting microwaves through the atmosphere without losing too much.
Okay, so let's unpack this study because it challenges all that. The researchers basically argue the biggest roadblocks aren't technical or even orbital.
No.
They're down here. Logistical, geographical, ground-based problems. They actually call it the grounding reality of space power.
That's the crux of it, yeah. They modeled the whole thing systematically, looking at 4 different scenarios. They started with just pure space, very theoretical, and then layered in more and more real-world limits.
So our plan here is to follow their steps, go through these scenarios one by one, and really understand why the ceiling for space solar power seems to be set by things like land use and electrical grids, not rocket science.
Exactly. It turns out the real bottleneck forces us to look down at the Earth, not up at the stars.
Okay, let's start at the beginning then. How do they set up this calculation, the methodology?
So the goal was precise. They weren't after a vague guess. They wanted the maximum possible power delivered by a fleet of SBSP satellites in geostationary orbit.
And GEO, just a quick reminder for you listening, that's the orbit about 36,000 kilometers up. Satellites there orbit at the same speed the Earth turns.
Meaning they appear fixed over one spot on the ground, which is vital if you want to beam power down continuously to the same receiver.
Makes sense.
So their whole calculation really boiled down to 2 main questions, which kind of gives us a roadmap. First, how many satellites can you physically fit into that GEO ring, given the rules of the road up there?
Okay, the physical space available.
And second, for each of those satellites, how much power can actually make it down and get fed into our existing electrical grids, considering all the losses along the way?
Right. So starting with that first question, how many satellites fit, they needed some kind of rule for spacing them out.
Exactly. And they applied one single, consistent constraint across all their orbital scenarios. The minimum distance angle, or MDA.
MDA. Minimum distance angle.
Yeah, it's the smallest angular gap you need between any 2 satellites in GEO. It's there for 2 main reasons. One is obvious, to stop them physically crashing into each other.
Definitely want to avoid that.
But maybe even more critical for these high-power systems, it's about preventing radio frequency interference. You can't have these massive microwave power beams crossing or messing with each other or with existing communication satellite signal.
Ah, okay. So it's not just about collisions, it's about signal integrity, too. What angle did they actually use?
They use 0.1 degrees, which, sounds incredibly small.
Tiny.
But when you're talking about the scale of GEO, 36,000 kilometers out, that translates into a huge amount of physical distance.
How much space are we talking about?
Well, they noted 0.1 degrees is actually pretty conservative. It gives a decent buffer. At that altitude, 0.1 degrees gives each satellite what they call an aperture range, basically a guaranteed clear zone of 147 kilometers.
Wow, 147 kilometers for each satellite. That's enormous.
Yeah.
How big are these proposed satellites meant to be?
Current designs are often talking maybe, 2 to 5 kilometers across for the solar arrays, somewhere in that ballpark.
So the required clear space is like 30 times bigger than the satellite itself.
Easily. That 147 kilometers accounts for all sorts of things. Potential drifting of the beam, small navigation errors, making sure heat plumes don't interfere, room to maneuver if needed. It's all about safe operations based on, let's say, cautious regulations.
Okay. So this MDA, this 0.1 degree rule giving 147 kilometers of space, that's a fundamental starting point for figuring out how many could theoretically fit up there.
That's the baseline physical and regulatory constraint for the space part of the equation before we even think about what's already there.
All right, so with that 0.1 degree rule established, let's look at their first couple of scenarios. These focus just on the orbital capacity itself.
Yeah, scenario 1 is pure theory. The absolute simplest calculation. You just take the full 360 degrees of the GEO circle and divide it by that 0.1 degree minimum separation.
Okay, simple division. What's the number?
The math gives you 3,600. Theoretically, you could fit 3,600 SBSP satellites into geostationary orbit if that was the only rule.
3,600. That's a lot of power stations. That's the absolute ceiling, assuming you could pack them in right next to each other with just that minimum clearance.
It's a huge number, yeah. It represents the sort of raw capacity of that orbital shell itself. But of course,
space isn't empty, especially not GEO.
Exactly. GEO is prime real estate. It's already got tons of satellites, communications, weather, military. They've been launching stuff up there for decades.
So that brings us to scenario 2. They had to account for the existing traffic, I assume.
Precisely. Scenario 2 models putting these new SBSP units into the gaps around all the existing satellites already operating in GEO.
Still using the same 0.1 degree spacing rule.
Still using the same 0.1 degree MDA clearance from any neighbor, whether it's another SBSP station or an existing comms satellite. You have to play nice with everyone already there.
Right. And does that make a big difference? How much does the number drop?
It makes a significant difference, as you'd expect. Accounting for that existing orbital congestion, the total potential number of SBSP satellites falls from 3,600 down to 2,509.
Okay, so a drop of nearly 1,100 potential spots just lost to existing traffic.
That's right. Almost a third of the theoretical capacity is already, in effect, occupied or blocked.
Still, 2,509 is a very substantial number. If that was the end of the story, if orbital slots were the only real constraint,
then yeah, the focus would just be on launch costs, manufacturing, deployment speed, that sort of thing. How do we fill those 2,500 slots efficiently?
But this is where the study takes that turn, right? This is where it gets really interesting because the focus shifts completely down to Earth.
Exactly. If space was the only limit, we'd be talking about 2,509 stations. But the researchers then start layering on the terrestrial realities, and this is where we see that the Earth's own limitations, not orbital physics, are really what dictate the final number.
So let's move to scenario 3. What's the first big ground-based problem they introduce?
Scenario 3 brings in the absolute necessity of the ground station, the receiver. It's usually called a rectenna.
Rectenna, rectifier, and antenna combined.
Exactly. It's this huge facility on the ground that has to capture the microwave power beam coming down from space and convert it back into usable electricity for the grid. Without a rectenna site, the satellite is useless, just orbiting hardware.
And these rectennas, they have to be pretty enormous, don't they, to catch that beam efficiently?
Massive, which leads directly to the first set of major geographical constraints the authors applied. They identified 3 big ones dictating where you could even possibly put one of these things.
Okay, what are they?
Constraint number 1 is pretty straightforward. For now, rectennas have to be built on land, not over the ocean.
Okay, that immediately rules out, what, 70% of the planet's surface?
Pretty much. A huge limitation, especially since many optimal orbital slots might be over the Pacific or Atlantic.
Right. What's constraint 2?
Constraint 2 relates to the basic geometry of GEO. Since those satellites are parked directly above the equator.
They have to be received near the equator, too.
Pretty much, yeah. There's a limit to how far north or south you can realistically place the rectenna. The study constrained placement to within 30 degrees of the equator, latitude 30 north to latitude 30 south.
Why that specific limit? What happens if you go further away, say, to 40 or 50 degrees latitude?
Well, the geometry gets difficult. From a satellite directly over the equator, the beam coming down to a receiver at a higher latitude has to travel at a much shallower angle through the atmosphere, almost skimming the horizon from the satellite's perspective.
Okay, and that causes problems.
Two big ones. First, the longer path through the atmosphere means more potential for energy loss, scattering, absorption. But the bigger issue is beam spread. That shallow angle means when the beam finally hits the ground, it's spread out over a much, much larger area.
Which ties into the third constraint, I'm guessing, land use.
Exactly. Constraint 3, beam size and land use. The further your rectenna is from the equator, closer to that 30-degree limit, the bigger the beam print is on the ground.
Meaning you need a bigger rectenna.
You need a vastly larger clear land area for the rectenna to capture that diffused energy efficiently. We're talking possibly 10, maybe even 15 kilometers wide in some of those higher latitude cases, just finding that much completely unencumbered land.
And it has to be accessible near the equator, not already used for cities or farms or protected nature reserves.
Right. You need huge plots of suitable real estate.
Also, putting those three things together needs to be on land, needs to be within 30 degrees of the equator, and the required land area gets huge near that limit. How much did that reduce the number of possible stations from the 2,509 we had in scenario 2?
This is where the numbers really start to fall. Applying just those terrestrial geographical constraints drops the number of potentially viable stations all the way down to 1,771.
Wow. From 2,509 down to 1,771. So that's another, 700 plus potential sites gone just because of geography and land availability?
Exactly. It proves pretty starkly that finding the right spot on Earth is already a much bigger constraint than finding a slot in orbit.
It really reframes the problem, doesn't it?
Right.
It becomes less about space engineering and more about, global real estate and land management policy. Finding 1,771 suitable massive plots near the equator.
It's a massive geopolitical and logistical challenge, and incredibly, that's still not the tightest bottleneck they found.
There's another level. Scenario 4.
Scenario 4 introduces what turns out to be the most restrictive constraint of all, and maybe the most insightful one. It's the bottleneck caused by existing electrical infrastructure.
Okay. So finding the perfect, huge equatorial plot of land is pointless if you can't actually plug the power into the grid there.
Precisely. You need the infrastructure, the high-capacity substations, the heavy-duty transmission lines, the distribution networks capable of handling a sudden, massive influx of power. We're talking gigawatt scale per station.
Right. You can't just plug a power plant's output into local neighborhood power lines. It would blow the system.
Exactly. It would overload everything instantly. So the challenge for the researchers was, how do you measure or estimate where that kind of heavy-duty grid infrastructure already exists? They couldn't map every power line globally.
So they needed some kind of stand-in, a proxy?
They did.
Yeah.
They used a really clever, though quite restrictive, proxy metric. They decided to limit potential rectenna locations only to areas that already have a significant level of human development measured by population density.
Population density as a proxy for grid capacity. What density level did they use?
They set the threshold at 3,000 people per square kilometer.
3,000 people per square kilometer. So that excludes, most rural areas, even if they were geographically perfect.
It excludes huge swaths of land, yes. The thinking is pretty logical, though. An area with that kind of density, think maybe dense suburbs, the edges of large cities, maybe very intensely farmed areas, is highly likely to already have the kind of sophisticated, high-capacity electrical grid needed.
Because serving that many people already requires significant power infrastructure investment over decades.
That's the rationale. They basically assumed that you wouldn't build the massive grid upgrades needed just for an SBST station. The power has to land where a robust grid already exists or is very nearby. If the density is lower, the local grid is probably too weak to handle a sudden gigawatt input.
Okay, that's a major constraint. So when they applied that rule, only placing rectennas in areas with 3,000 plus people per square kilometer on top of all the previous orbital and geographical limits. What happened to the number?
This is where the number just collapses. The final, most restricted count of potential, fully viable SBSP stations, considering all the constraints, orbital traffic, geography, land use, and grid readiness, it drops to just 364.
Wow. 364, from 1,771 down to 364.
A huge drop.
That's an almost 90% reduction from the original theoretical maximum of 3,600 in scenario 1.
It is. 89.9% reduction, to be precise. The orbit could hold thousands, but Earth's current infrastructure, using their proxy, can only really support receiving power at 364 locations.
So the conclusion seems pretty unavoidable then. The ultimate limit on SBSP capacity, at least based on this analysis, isn't set by space. It's set by the ground, specifically by where we've already built dense populations and high-capacity power grids.
That's the core finding. The bottleneck isn't rocket science. It's city planning and electrical engineering, essentially.
Okay, so we have the final, most constrained number, 364 potential stations. Now, what about the second part of their calculation? How much power could this constellation actually deliver?
Right. So first, they had to estimate how much power each station could collect in space before you account for all the losses getting it down here.
What assumptions did they make for that?
They used a few key variables based on plausible near-term technology. They looked at the solar panel area, the efficiency of the cells, the angle to the sun, which is pretty constant in GEO, and the solar irradiance up there.
How big did they assume the solar panels would be?
They assumed a very substantial area, 10 square kilometers per satellite.
10 square kilometers. That's hard to even picture. What's that equivalent to?
Let's see. It's roughly 1,400 standard football fields. Or think about the entire area of a major international airport complex. It's truly enormous.
Okay, massive scale. And the efficiency.
They assumed a 20% conversion efficiency for the solar cells themselves, which is pretty reasonable, maybe even a bit conservative for future tech, but achievable now.
So 10 square kilometers of panels at 20% efficiency in constant GEO sunlight.
Mm-hmm.
How much power does that collect per station?
The number is staggering. 272 gigawatts generated in orbit per station.
272 gigawatts.
Yeah.
Each. If you could get even a fraction of that down.
Exactly. If all 364 stations collected that, you're talking almost 100,000 gigawatts collected in space.
Right.
World energy solved, right? But
here come the losses. This is the big question mark, isn't it? Converting that DC power to microwaves, beaming it 36,000 kilometers, getting it to the atmosphere, catching it, converting it back to AC.
This is the critical step. And honestly, the point where the authors applied really extreme conservatism.
How much did they estimate would actually get delivered to the grid out of that 272 GW collected?
Their final estimate for power delivered to the grid per station was just 1 gigawatt.
1 gigawatt delivered from 272 gigawatts collected.
Yes.
Wait, that's an overall efficiency of what? Less than 0.5%? Around 0.3% or 0.4%?
0.37%, yeah.
Yep.
It's an incredibly low number. It implies absolutely massive losses in the conversion, beaming, atmosphere transit, and rectenna conversion process.
That seems almost unrealistically pessimistic. Does the paper justify that huge loss factor in detail? Mm-hmm. Or is it more of a placeholder for we expect very large losses?
It's acknowledged in the source material itself that this assumption is extremely conservative and lacks extensive, detailed justification within the paper. They were effectively building in the largest possible buffer against any technological optimism regarding transmission efficiency. It assumes a near total loss.
Okay, well, let's run with our ultra-conservative number for now, just to see where it leads. If you have 364 stations and each only delivers 1 gigaW to the grid,
then the total power provided by this worst-case constellation is 364 gigawatts of reliable baseload power.
364 gigawatts globally. How does that compare to, say, total world electricity consumption?
It works out to be enough to cover approximately 3% of total global power usage.
3%. After all that effort, 364 massive satellites, huge ground stations, 3%, doesn't immediately sound like a game changer. Why is that figure still considered significant enough for companies and countries to be pouring money into this?
That's a fair question. The key is that it's baseload power. It's not intermittent like wind or ground-based solar. It's 3% that's available 24/7, constantly, reliably, regardless of weather or time of day.
Okay, so it's about the quality and reliability of that power, not just the raw amount.
Exactly. In global energy markets, adding 364 gigawatts of perfectly predictable, stable power is actually transformative. It helps stabilize grids, reduces reliance on fluctuating sources, and can displace a significant amount of fossil fuel generation used for baseload.
Especially, I imagine, in those equatorial regions where the rectennas would be located.
Absolutely. For developing nations in that equatorial band, having access to even a fraction of this reliable power could be profoundly important for energy security, industrial development, and meeting climate goals. So, yes, 3% globally might sound small, but its impact could be very strategically significant.
That context is crucial. Okay, so even with the most pessimistic assumptions, it still seems to offer a notable benefit. But we definitely need to circle back and question some of those assumptions, right?
Oh, absolutely. Critical thinking is essential here. And it's worth remembering the authors themselves acknowledge their bias as being huge SBSP fans.
Right, they weren't trying to kill the dream.
No, quite the opposite. Their rigorous approach just led them to these conservative numbers when they stuck strictly to current limitations and cautious estimates. But it highlights where the potential upside is.
And the biggest potential upside seems to be in that transmission efficiency. That jumped from 272 gigaW collected down to 1 gigaW delivered.
Without a doubt. That 0.37% end-to-end efficiency is the single most impactful conservative assumption. If future technology, better microwave generators, more efficient rectennas, maybe optimized frequencies can improve that, the whole picture changes dramatically.
Let's just play with that for a second. What if, instead of 0.37%, the efficiency was, say, still low, but maybe 1%? So 1% of 272 GW gets delivered.
Okay, 1% of 272 GW is 2.72 GW per station.
Right, so now you have 364 stations, each delivering 2.72 GW instead of 1 GW.
That takes the total constellation output to just under 1,000 gigawatts. 3664, 2.72, and like 990 GW.
Almost a terawatt.
Yeah, which is nearly triple their original estimate. Suddenly, you're not talking 3% of global power. You're pushing up towards maybe 8 or 9%.
Okay, now that starts to sound like a global game changer. 8 or 9% of the world's baseload power coming reliably from space. That would reshape energy markets and decarbonization efforts.
Completely. So improving that transmission efficiency is probably the single most important technical challenge for making SBSP truly revolutionary.
What about the other constraints? The orbital spacing, for example. That 0.1 degree MDA, giving 147-kilometer clearance, seemed quite large.
That's another area potentially ripe for change. If future autonomous control systems, better tracking, and maybe international agreements allowed for tighter spacing, say, having that clearance safely, you could theoretically double the number of orbital slots right away.
From 3,600 theoretical max to 7,200.
Potentially. Of course, that immediately runs back into the ground constraint. Could Earth actually find places for and handle the power from thousands more rectennas? Which brings us back to those terrestrial limits.
Ones that caused the biggest drop, from 1,771 possibilities down to just 364. Mainly that population density proxy for grid infrastructure.
Exactly. We need to question how rigid that constraint really is. Using 3,000 people per square kilometer effectively biases the whole system towards places that are already heavily developed.
Right. Often wealthier nations that built out their grids decades ago. It implicitly assumes that a developing nation, even one perfectly located near the equator, wouldn't build the necessary grid upgrades specifically to receive this cheaper, cleaner power from space.
Which seems like a questionable assumption in the long run, doesn't it? If SBSP becomes cost-effective and reliable, wouldn't that be precisely the catalyst needed to drive new infrastructure investment in those ideal locations?
You'd think so. Why couldn't you build a rectenna in a less dense area, maybe farmland acquired for the purpose, and build the necessary substation and high-voltage lines alongside it as part of the project?
Or even revisit the idea of offshore rectennas, which the study dismissed for now. If you could overcome the technical hurdles there, it opens up vast areas, lifting that infrastructure constraint, allowing for greenfield development driven by SBSP.
That could potentially push the number of viable sites back up from 364 much closer to the geographical limit of 1,771, or maybe even beyond if offshore becomes practical.
It really could. So what's striking is, even with all these layers of conservatism, the huge transmission loss, the wide orbital spacing, the rigid rules about where rectennas can go, the study still finds SBSP could provide a significant 3% of global power.
Which implies the true potential, if some of those ground-based bottlenecks are addressed or technology improves, is actually much, much higher.
Precisely. The study doesn't kill the potential, it just relocates the main challenges. It says the potential is real, but the current roadblocks are largely terrestrial, logistical, infrastructural, maybe political, things that we can theoretically work on down here.
It suggests maybe investment shouldn't only focus on launch costs and satellite tech. Maybe investing in grid upgrades in strategic equatorial regions is just as important, maybe even more so, to unlock SBSP's future.
It definitely shifts the strategic focus. You need both space capability and ground readiness.
Okay, so let's try to pull this all together. We started this journey looking at the possibility of thousands of power stations in orbit, 3,600 theoretically.
Which dropped to about 2,500 once you factored in existing satellite traffic. Still a huge number.
But then the constraints shifted to Earth. Geography, the need for land near the equator, cut it down to around 1,700.
And finally, the need for existing high-capacity grid infrastructure approximated by population density brought the number crashing down to just 364 viable stations in the most conservative scenario.
The undeniable takeaway seems to be Earth's ability to receive and use the power is the limiting factor right now, much more so than our ability to put solar panels in space.
It's the grounding reality, as they put it. The future of this potentially revolutionary space technology hinges on our willingness and ability to upgrade our infrastructure here on the ground.
Which really changes how we should think about planning and investment, doesn't it? If the grid in equatorial regions is the main bottleneck, does improving that grid become a necessary first step before we can fully utilize advanced space tech like SBSP? It ties space exploration directly to basic economic development on Earth.
It's a fascinating link. The most advanced, futuristic energy source imaginable is currently held back by things as mundane as land zoning regulations and the capacity of existing power lines.
Which leaves us with a final thought for you, the listener, to maybe mull over. If the biggest constraint on this incredibly advanced orbital system is actually the existing infrastructure right here on the ground, what are the ground realities, the infrastructural limitations in your own field or area of interest? Could existing networks, standards, or physical logistics be quietly holding back the next big innovation?
It's a great question, because sometimes, as this analysis shows, the hardest part isn't figuring out how to build the amazing new thing. It's making sure the roads, the pipes, or the power outlets are ready for it when it arrives.
Definitely something to think about. Thanks for exploring this with us today.
My pleasure.
We'll talk to you next time.